You've got to remember that this is called a circle.
Come on in, everyone. Still got about 3 more minutes. Yeah, be quiet. right. Got another person coming in. Okay, does anybody have any questions before we get started? Looks like 7 of you are in here anyways. It's not the best number, but we're gonna have to press on because it is 5:20. Any questions about past material? We did some pretty tough integrals last time. I showed you how to use basically the electric field equation that I created for a vector form. So it actually gave you a vector form of the differential electric field. And I also then use that to calculate the electric field due to a infinite line of charge. I think I did a ring and then a disk after that. But now today we're going to show you another way using Gauss's law that should make it quite a bit easier. That was not it. I'm actually trying to look to make sure I'm remembering everything correctly. So that date would have been the 21st, I think. Let's see. Yeah, it looks like I went up to there. Then I did the disk. Yes. So that was it. We did the last thing was the disk. And in fact, when I got the disk, I ended up getting sigma over 2 epsilon naught times square bracket 1 minus 1 over the square root of z squared plus r squared, close square bracket, k hat. So if you consider that in the limit of z being very small compared to r, then you end up getting the electric field near a disk of charge is sigma over 2 epsilon naught. That's basically what we're going to show today. So hopefully that makes some sense. So before I move on, does anyone have any questions? Okay. I wanted to let you know, let's go ahead and share my screen for a second. I'll do this one. So I put up week 6, and in week 6, I want you to see I have electric flux, a calculation of a surface integral. That's something you need to be able to do. It's something that we use and we discovered was very important in electricity and magnetism. We discovered it was very necessary in electricity and magnetism, both in terms of the electric field flux as well as the magnetic field flux. Both turn out to be important. That is a big concept. That's a vector calculus concept. If you were, say, fortunate enough maybe to take Calc 3 at Princeton, Harvard, or MIT or something like that, they might actually get to that. Most places do not in general get to that, or at least most of the places I've interacted with, most of the universities I've interacted with never get to that kind of stuff. There's a whole nother branch, like some schools will actually use the differential forms for their 3rd semester of calculus. So there's some more mathematical, more quote unquote, possibly elite schools that do that kind of stuff. It's in your book. You can find it in your calculus book, but they do surface integrals, line integrals, path integrals is another word for line integrals. They'll do a generalized chain rule, which involves a matrix called the Jacobian, all sorts of cool stuff. But you normally don't get to cover that. And that's normally the typical scenario with people that major in engineering or physical sciences. A lot of times you end up learning your math not from your math instructors, but rather from your physics instructors or your engineering instructors. So I've put a video there. I'll give you a little bit of a talk about it. And then we're going into Gauss's law, which is another way of calculating. Well, it's a lot of things, but one of the things that we use it for in this course is to calculate electric fields that have a rather high degree of symmetry. So I wanted you to see that. I also wanted you to see that up here, I did fix the practice, the chapter practice. So a lot of these had dates on them and they were old. And then some of them just didn't have questions in them. And I'm not sure why, but sometimes when you copy a test over, it doesn't copy the questions. Man, I can't stop yawning. I know I'm making y'all yawn. I apologize. But anyways, I've done up through chapter 21 now. I'll be doing 22 by the time we get to 22 and 23 by the time we get 23, so on and so forth. But these are available to you now, and they're really good help. They're basically 3 problems and 1 concept question every time you take it. And every time you take it, you'll get a different set. So anyways, I just wanted to show you that. What I'm going to do now is I'm going to share my screen so we can talk about electric flux. And electric flux is something that, like I said, it was discovered probably in the late 1700s and in the early 1800s, that this quantity, this flux really mattered, both in terms of electric field flux as well as the magnetic field flux. We'll use the magnetic field flux in Faraday's law, and we'll use the the electric field flux in Gauss's law. So let me share my screen using my iPad. I've got that. Now I've got this up here, and I'm actually looking at the wrong screen right now, but I will change it directly. So yes, I evidently closed the wrong thing. Let's kill that. Let's go back to this guy. All right. Hopefully that should come up in a second. Let me double check, make sure it's still, yeah, it still appears to be doing it. Okay. So there turns out to be something that the founding fathers of electricity and magnetism, that would be people like Michael Faraday, Galvani, Hertz. Well, Hertz is actually a little bit later, but Maxwell, he was a little bit later as well, but he preceded Hertz in terms of his discovery. And these type people discovered that this thing, they realized they were starting to get the idea that there might be some sort of tentacles that reached out over space, and those they literally pictured them as if they were real sort of tentacles or something like that. Now, I don't think any of them used the word tentacle, but basically what they were looking at was sort of like little webbings or fingers or strings that were out reaching out into space, and they actually imagined them as real things. So the electric field around the point charge, if the charge was positive, would have these little fingers pointing out of the charge in every direction. And of course, the more of those little fingers there were per unit volume, the stronger the electric field was. And what they realized is a important parameter with regards to those little tentacles is how many tentacles would go through a certain surface area perpendicular to that surface. So if you had, for instance, a window pane, you could have a window pane like this, and things come at some angle other than perpendicular, and they cared only about the component of that tentacle that was perpendicular to the field. So this little part right here would matter. So with that came the idea of using this concept called flux, and we use the symbol, the Greek symbol phi, or the Green Lantern symbol. And we don't have to do it right now because we haven't actually discussed any other types of flux, but in general, a flux can be an electric flux, so we subscripted E. Later, we'll subscript it B for the magnetic flux. And the first order approximation, that's why I'm putting approximately equal, really is just the strength of the electric field times the size of the area through which it goes times the cosine of the angle between them. And what do we mean by that? Well, if you imagine, for instance, that we had a window, say, that electric field lines were going through, we could say this is the window, and this is the window. So like that. Okay. And of course, this means that basically this is sort of lines parallel and actually on the window. You could imagine, for instance, if we took a vector perpendicular to that surface, which would also be perpendicular to this line, that vector A could be represented that way. And the argument is basically there's an infinity of vectors that lie in that plane, And you can't make a good argument for any of them being representative of the area, because there's really no reason to choose one pointing to the right as opposed to one pointing up, as opposed to one pointing down as one pointing to the left, or at 45-degree angles. But if you step out of that plane, which you can think of as the front of your phone, you can imagine that the front plate of your phone could be represented by a vector that points perpendicular to the face, like this, or another one like that. And there's really only two that are reasonable. There's a vector that points that way, and then there's a vector that points that way. So you reduce the ambiguity of it down to just two, especially if you're just not really concerned much about the magnitude. So it seemed obvious that the best choice would be represent the actual area A by a vector A that's perpendicular to the surface. And the only ambiguity is whether it's perpendicular, like this one shown, up, or if it's perpendicular, let's say, like this one back here, down. Okay. And if you ultimately turn your attention to only objects that are closed surfaces, meaning they're the outer surface of something that clearly has an inside and an outside, then you can remove that ambiguity by arbitrarily saying the vector should actually point from the inside towards the outside. So then if this was part of a larger surface, for instance, then this blue one would point from the surface towards the outside as opposed to towards the inside. Either one's equally valid, but they chose to do the one that points out. And then what you get is a flux that's positive when field lines are piercing from the inside out, and a flux that's negative when they're piercing from the inside in, or from the outside in. So we have that vector A, whose literal magnitude, like if this, for instance, if this window were, say, A units wide and B units long, then the magnitude of that vector would actually be A times B. So it literally has a unit or a magnitude that's equal to the area. And then you could take and say, well, let's imagine an electric field line coming this way. If you do that, then these two vectors are tail to tail, and that's the angle theta that we're talking about. Okay, that's really what the electric flux is. But it turns out that's just a first order approximation. So that works really well if the surface is really flat and the electric field doesn't vary very much over the entire surface. If you want, in general, this to be applicable, it turns out the better explanation of what the flux is the flux is equal to the integral of E dot dA, where again the dA this time, since it's got a differential in front of it, it's a very small segment of area, and you choose it small enough maybe that so the surface is completely flat over the the specificity that you want, and the electric field is completely constant over that entire surface. Then you've chosen dA small enough, and you can just take the dot product like you did the regular part. So if that's the case, then you can imagine a three-dimensional shape, let's say like a kidney bean or a jelly bean or something like that. Your three-dimensional shape would look like this. Something like this. And you could actually imagine, of course, it's got lines going this way as well. And these, of course, would go around this way. This one would go around this way, so on and so forth. But you could imagine, for instance, a little differential area element, say, right here. And that could be represented by a little blue vector. And I don't know why my lines got fat. Oh, no, I do. I touched that button. So this could actually be the differential area vector, that little guy right there. That could be dA, and it's actually perpendicular both to this surface line and that surface line, showing it is in fact perpendicular. And then at that particular point, you might actually have the electric field going this way, pointing out. And again, that would be theta. And you could do that over, various areas and get this ultimate result for the electric flux. So this quantity is called the electric flux. And by taking that dot product of E with the dA, you're basically taking the E and multiplying it by the cosine of theta. And I think you can see, if you imagine making a right triangle with these black lines, then and that red line being E, of course, then you could see that E cosine theta is actually the component of E that is parallel to dA vector. And that's the whole point, is we want to use that dot product to pick out components that are parallel to the dA vector. So you're really just finding the components of the electric field that are penetrating the surface perpendicularly to the surface. Okay. So that's basically the scenario here. And now I'm going to use that to give you an idea of how to calculate it. So what you could do, for instance, is we can draw a coordinate system. And we could draw a coordinate system like this. That did not turn out so well. Coordinate system like that. No, that's not the one I wanted. No wonder. Excuse me, like this and like this. And now this would be, for instance, our x-axis, and this would be our y-axis, and this would be our z-axis. And now we could imagine a little shape in here. Let's say this shape right here. And let's say this shape, which goes over 4 over here. And let's imagine this shape right here. So you can actually imagine a cube, if you will, or a rectangular shape, if you will, that clearly has both an inside and an outside. That's sort of the whole point of this, is if you make an inside and outside, then you can non-arbitrarily define the actual direction of the dA vector in a non-ambiguous way. So that's what our little closed volume is, for instance. Now let's imagine for a second that you had an electric field, let's say E. Oops. Let's just erase all that because I left it on making it neat. So let's imagine we had an electric field that is actually a function of X, Y, and Z. You could actually have a Y component, for instance, that depended on, let's say, 2y, 2y times x j hat. Okay, that's just supposedly a somewhat arbitrary electric field. Okay, now when I go to do this, I have to actually calculate the total flux. So the question is, what is the total electric flux of E through the surface of that rectangular shape? Okay, so what we do is we go by and say, all right, let's name these surfaces. I'm going to name this leftmost surface 1, And then I'm going to name this front surface, surface 2. And then I'm going to name this this rightmost surface, surface 3. And then this back surface, I'm going to label it 4. And then I will need to do the bottom surface, which I'm going to call 5. And then the top surface, which I'll call 6, like this. Okay. So those are my surfaces. And then to actually compute this, I have to one by one figure out what all the parts of this integral are for each of those surfaces. So I have to calculate, for instance, here's my solution. I have to calculate notice I put a circle on that. It turns out Gauss's law only applies to a closed surface, and we now have a closed surface. Basically, the outer surface of this rectangular shape is closed. And to remind us that, we write a circle on the integral, and that tells us so. So here's the E dot dA, and that's equal to the electric flux, which is what we're trying to calculate. So that's what we're doing here. I'm losing my voice. All right, so first off, I'm going to take surface 1, and I see that for surface 1, X is going to range from, let's say this number right here is 2.00 centimeters. Let's say this number right here is 4.00 centimeters. And let's say this number right here is 3.00 centimeters. It's not necessarily that good a scale, but the main thing is we've got numbers, so that's fine. And now I can see that X on surface 1 ranges from 0 to 2 centimeters. Dang it. From 0 to 2 centimeters. I'll leave off the units there. Now I got to look at Y. Now, Y for that one surface is actually a constant, and Y is equal to 0. And then Z is going to range from 0 to 3.00. Okay, so now I've evaluated each of the variables X, Y, and Z. The integral involves an E, so I've got to evaluate E on 1, which I'll call E1. And of course, E1 should be 2 times 0, because that's Y, and then times X, which in this case, we saw X varied from 0 to 2, so I'm going to say 2YX. And actually, let me make it a little more fancier. I'll put a 2 there, so it's Y squared. So for this guy, I'm going to put a 0 squared there. And then it's going to be, in fact, J hat. So that's what the electric field is completely on that surface. Now I also need to figure out what dA is on that surface. And dA needs to be a unit vector, needs to be a vector that's perpendicular to that surface. And I need the integrand not to change too much over the entire surface. Well, we see that the electric field depends on Y and X. So since it depends on X, I need to make X very, very narrow. So what I'm going to do is choose for my differential area element is this narrow little vertical slice whose width is dx. And then, of course, whose height is actually going to be 3.00 centimeters, because that's the height of the Z. So ultimately what that means is dA is going to be 3.00 technically centimeters times dx, and it's going to point in the negative J hat direction. Okay, because it's got to point out of the box. The box, the inside of the box is to the right of surface 1. Therefore, we have to point it to the left. That's why I've got a negative. So now I can do the integral over 1 of E dot dA.
which I can subscript E1.dA1 if I wanted to, which I did. And in this case, I'm going to get the integral of 0 j hat dotted with negative 3.00 dx j hat, but that 0, of course, and of course, this is going to run from x equals 0 to 2.00. That's going to end up giving me just plain 0 because the electric field was 0 on that end. You can see that for surface 2, notice surface 2 is the front side. So if I tried to do surface 2, I would say E is equal to basically dot, dot, dot j hat. At the same time, I'd also see that dA, in other words, I'm skipping some of the steps because there's part that's going to be crucial here. The dA in this case has to point towards us, and that's going to be in the positive I hat direction. So E dot dA is going to equal 0. So I don't need to do that. When I do surface 3, E is going to be dot, dot, dot. Oh, actually, this surface 3 is a good one. So I'm actually going to take a little bit more time and do this. So let me kill that real quick. But I think you can see that surface 4, so let's say IV, the integral goes to 0. And that one, you see it's the case because 4 is going to have a dA that points in the negative I hat direction and a E that points in the J hat direction. And then we'll see that 5 is going to have an integral. In that case, 5 is the one that's the bottom surface, and the bottom surface is going to have a dA that points in the negative K hat and E points in the J hat. So that's going to be 0. And then finally, we get 6. And 6 is going to have an integral that goes to 0 as well, because 6 is going to have a positive K hat, and the E is going to be a J hat. So really all we have left now is surface 3. So I'm going to do 1, 2, 3, and the integral over 3 of E dot dA. In this case, the Y is actually equal to 4. So it's going to be 2 times 4.00 squared times X in the J hat direction, dotted with dA. Again, I'm going to do dA the exact same way. So there's my dA vector. And that is, in fact, going to equal, the height would be 3.00 centimeters times dx. And, of course, this one's going to actually point in the J hat direction. So I'm going to get 3 dx j hat for that. 4 squared is going to be 16. 16 times 2 is 32. And then times 3 would be 96. So I'm going to get equals, oh crap. I'm going to get that it equals the integral of 96 x. J hat dot j hat gives me 1. That's the integral of dx from 0 to x is 2. So up to 2. So this is going to be integral of x is 1/2. Half of 96 is 48. So that'll be 48 times 2 squared. So that's 4 times 48. That'd be 160, 192. And actually, that unit comes out to be newtons per coulomb for the electric field times the centimeters squared. It's normally newtons per coulomb meters squared, but the main thing is that's what it came out to be. So that's a really quick version of how to do a surface integral.
If you want to see a more stringent one, then look at the actual videos I linked to in week 6 module from my YouTube channel. So check that out. Anybody have any questions on what happened with all those surfaces? So do y'all understand why I made the segment DA, why I made it differentially wide or infinitesimally wide in the X direction as opposed to the Y direction or the Z direction? That's key to understanding how you do this, because you can't have the electric field or the DA varying very much over the entire differential section. Specifically in this case, the electric field. So since the electric field depends on Y and X, luckily the Y had a very specific value at side 1, namely 0, and at side 3, namely side 3 was Y equal 4 centimeters. So that automatically fixed the Y from varying too much, but the X could go from 0 to 2. That's a macroscopic measurement, not an infinitesimal one. So all we had to do was find a differential area that we could add up to make the total area. And therefore I chose a slice that was dxy by basically 3 centimeters tall. So that's why it's 3dx. And then of course it's got to be perpendicular to the surface. So it either had to be in the positive j hat or the negative j hat direction. But since it was surface 3 and it's a closed surface, that has to point as if it's coming from inside the box. So it had to point to the right. Any questions on that? Okay, you'll see your book does actually have some. So if you look in the problems at the end of the chapter, you'll see it has some actual flux problems. You'll see as you're taking the chapter 22 practice, you're going to see some flux problems. As you're taking the practice test, you're going to see some flux problems. And if I remember correctly, I think there's one in the homework set as well. So be prepared to do that. A lot of them will be a lot easier, but I gave you some pretty a little bit more rigorous and stressful flux calculations in the videos that I posted on my YouTube channel. So I think I linked 3 or 4 of them in week 6. So anybody have any questions on that before we move on? Okay, it looks like we're all good on that. Actually, let me go ahead and make sure my chat box is available too, so in case somebody's chatting with me as opposed to speaking. Okay, I've got the chat window open now so I can see if anybody types anything. And it appears that no one has typed anything, so we're good on that. All right, so let me show you a very interesting example. And this example is going to be an example that we can do for a very specific case that we can work out, but it's going to give us the answer that's actually can be generalized to the true answer. And in that sense, we're deriving Gauss's law. So let me draw another coordinate system. I'm going to draw a coordinate system right here. I've mentioned this to you before, so make sure you remember your coordinate systems always have to be in a right-handed coordinate system, which means if you take I hat and cross it with j hat, it better point in the direction of k hat. And that is, of course, is given by a right-hand rule by understanding how cross products work. So you got to make sure your coordinate system's right-handed. Other than that, you're pretty much free to do what you want. So I'm going to create, in this case, coordinate system x, y, z. And what I'm going to do is I'm going to put a charge at the origin. And that charge is going to be just a charge q. Okay. It's a point charge, or you could imagine it to be a finite charge, but the main thing is it's spherical. So it's centered on the origin. It doesn't look like it's centered on the origin because you can't make but for so
perfect of a figure, but it's supposed to be. So we're going to pretend like it's perfectly centered on the origin. So let's say, imagine, whoa, okay, so let's not write that evidently. So imagine a small spherical charge centered on the origin and the charge is Q. Okay. Now, can anybody tell me if there's a charge Q there? Can anybody tell me what the electric field strength would be a distance r away from it? Anybody? Okay, no answers. So the electric field, according to Gauss's law, of either a point charge Q or a spherical distribution of charge Q is given by E is equal to Q over 4 pi epsilon naught r squared, where r is the distance between the point charge Q and the location of the point at which you wish to know the electric field. So that's actually how you calculate the electric field. That's the formula. So that should be the strength of the electric field. And we should remember that the electric field is defined to point in the direction that a positive charge feels a force if it was located there. So for instance, we might imagine 3, 4. We might imagine that right here on that blue dot, a distance of, let's say, 4 meters away, that could be the point at which we wish to know the electric field. So I just take Q and I divide it by 4 pi epsilon naught times 4 meters squared, and that would be the magnitude, but it would point directly away from, as if it left the center of the charge and went through that point right there. Okay, so it would actually point directly along the y-axis. If, on the other hand, I chose a point right up here on the z-axis, then it would point right along the z-axis in the positive direction, again, as if it came straight from the center of the charge Q and went through that point. And then finally, if I did here, then it would again be a electric field that would point as if it came from the center of the charge Q and went through that spot right there. So it's actually what we call radially outward. So you actually know that the electric field points radially outward. Now, what I'm going to do is I'm going to actually take the time and draw a sphere of radius 4, say, and that should look like this roughly. Okay, now that didn't turn out good, but I was trying to center it up, make sure I hit all the right spots so I could stretch it accordingly. And then let this draw the actual sphere perfectly. Okay, so that looks fairly good. It's not perfect, but I think you get what I'm trying to do here. So that should be the concentric sphere. And in fact, to further make it look like a sphere, I might draw this like that and that like this, so you can see it's an actual spherical surface. Now, I don't think that's very good, so I'm going to erase it, but I just wanted you to understand that that is a spherical surface, okay? In fact, when we use Gauss's law, we'll call the spherical surface that we create a Gaussian surface. Now, this particular Gaussian surface has a radius of r. And actually, I didn't like drawing freehand, so I did that. So there's the radius r right there. And it's concentric. So that's what I meant by concentric spherical shell. The reason why I'm doing this is because I want to find a electric flux, and I want to choose the perfect surface so that the electric field lines will everywhere be exactly parallel to the dA vector. So for instance, if we imagine, let me try a different color here. I'm going to try green. So we can imagine coming out some distance, say from the origin, from the origin out like this, okay, at an angle theta, say, and then, yes. Oh, okay. I thought somebody said something. Now I'm actually imagining this line lying in the XY plane, and I'm going to allow theta to increase by an amount delta theta, or d theta in this case. Okay. So this little amount right here is going to be d theta. Now I can imagine also following this up to a point on the surface of the sphere. And it's actually turned out really bad. I'm going to undo all that because I really need a little bit better drawing than that for you to fully understand. So I'm going to change my green lines and make them a little bit more obvious. Let's take my green lines instead and let it be here and here. This will be the angle theta, and this will be the angle delta theta. Okay. Now, if I imagine this going straight up to hit the outside edge of the sphere, what I can imagine is it's going to hit roughly like this. And then that's going to be on part of the sphere this way and make out this little shape like there. Okay, now that actually matters because this angle right here, that angle is called the polar angle phi. And if I allowed it to vary by delta phi or d phi, okay, then it would look like that. And in fact, you could trace this back and you'd see that this line goes to that corner and this line goes to that corner over there. And you could actually make out that this side right here is actually, it's sort of R, meaning this distance right here. Let me change this to black a second so we can make sense of it. This line right here. Dang it, why is it not drawing black? This line right here has a length R. Now, this line down here, on the other hand, that line does not have a length R. In fact, that line has a length R times theta, or excuse me, R times sine phi. So this length is R times the sine of phi. Does everybody see why that's the case? If that black line is R, then the green line, that's sort of its shadow down there, should really be R times sine theta, or sine phi, excuse me, not theta. So that's what that is. And of course, that's the radius of this little arc, the green arc that we're showing. So in fact, that little blue arrow that I've drawn right here, that length has a length of r sine phi d theta. And this little guy is the d theta I'm talking about. Now, the other one, the black line, had a length r. So what that means is this edge right here, and it looks like a rectangle, by the way. That's sort of the whole point. That line right there has a side given by r times d phi. So we can actually say that dA, which is what that little window is, if you will, dA is going to actually be r squared sine phi d theta, and it's going to point radially outward, and we'll just call radially outward by the unit vector r with a hat symbol, and the hat symbol just means it's a unit vector, and r means it's radially outward, meaning at any point in space, if you connected a line with the origin to that point in space, the radial vector would point along that line, but away from the origin, like this one does. So with that, we can now see that the vector dA is in fact this guy. So there is our dA vector. And notice that's exactly the direction that the electric field points. That's the whole point, is I've tried to make this look exactly like the electric field points. And now that I have that, I can calculate the flux like this. I think I decided to say the solution was in blue. So the flux is equal to the closed integral of E dot dA. Okay. We found that the magnitude of the electric field is actually equal to Q over 4 pi epsilon naught. Now we're actually on a surface of radius big R, so I'm going to call that R squared. Now it has to be a vector because I have a dot product there, and I just told you the direction is in the radial direction, so that vector is going to be represented by r hat. Notice by using a unit vector, I don't have to change the r squared in the bottom to r cubed like I did last time. So I now have that, which is the electric field. And now that is going to be dotted with dA. And the dA, like I said, is going to be r squared. I should put it back in blue. It's going to be r squared sine phi d theta r hat, like that. So that's actually the dot product that's happening in this integral. So I'm going to say, I'm going to remind you that the dot product is what we call a linear operator. So that means I can take all the stuff that's not vectors and write it out to the left like this. And this. And then all I have left is r hat dot r hat. So that's what it means to be a linear operator. That's part of what it means to be a linear operator. A linear operator means that if you have a scalar multiple, you can pull that in front. It also means if you have a sum of the two, you can separate the sum out. But in this case, we now have a r hat dot r hat, and this r hat dot r hat is in fact, it's a unit vector. So it's 1 times another unit vector. So that magnitude is 1 times the cosine of the angle between them. Well, they're identical vectors, so that's 0 degrees. And of course, the cosine of 0 is 1, so that's 1. So that's what the r hat dot r hat is. Now, we can go ahead and compute this integral as follows. For starters, we notice that the r squareds cancel out, and that the q over 4 pi epsilon naught is in fact just a constant. So I'm going to write q over 4 pi epsilon naught times the integral. Now, here's the part that might throw you a little bit, because I'm getting ready to do a multiple integral. In other words, a double integral in this case, because we're doing an area. Don't worry about it. I'm just showing you what it's going to work out to be. But basically, I'm going to erase everything, and that will just help. No, I'm not. So this is going to be the sine of phi d phi integral of d theta, and phi, it turns out, and these coordinates that we're using are technically called spherical coordinates, and that phi goes from 0 to pi, whereas the theta goes from 0 to 2 pi. So I'm going to integrate this from 0, well, let's say phi equals 0 to pi, and I'm going to integrate this one from theta equals 0 to 2 pi. Well, that's pretty straightforward. I get q over 4 pi epsilon naught. Of course, the derivative of cosine is negative sine, so the integral of sine is negative cosine. So I'm going to get negative cosine phi, and that's going to be evaluated from 0 to pi. And then, of course, the integral of d theta is just theta, so that's going to be evaluated from 0 to 2 pi. So now I've got q over 4 pi epsilon naught negative, because I took the negative from the cosine. Now I'm going to say the cosine of pi minus the cosine of 0, like that. And then I'm going to say 2 pi minus 0 is the other integral. Of course, the cosine of pi is -1, and the cosine of 0 is 1. So I got -1 minus 1, which gives me -2. And this part right here just becomes 2 pi. So I end up getting -4 pi, which cancels out with the 4 pi and the negative there. So ultimately, all I get is q over epsilon naught. Now, that's not a coincidence. In fact, that is the general formula. If you look at it, you'll notice q happens to be exactly the charge enclosed in the closed surface. So this is the charge enclosed by the surface. And it's just divided by epsilon naught. In fact, Gauss's law says that the closed integral of E dot dA is equal to Q enclosed over epsilon naught. Of course, you can also just reword that to say the electric flux over any closed surface is equal to the charge enclosed divided by epsilon naught. Then you don't have to actually write the integral, but that's really what it is. Okay, now the good news is you don't have to know any of that spherical coordinate stuff that I just showed you, or any of that kind of stuff. I just wanted you to see how it's actually done. You get to see a double integral. Yay, that's cool. That's something you'll cover in Calc 3. You get to see spherical coordinates. That's cool. That's something that will come in handy when you take dynamics. And you get to basically see sort of a proof, if you will. But now we're going to use that law. Now it's called Gauss's law. It's not called Gauss's helpful hint that sometimes works. It's really a law. But the weird thing is we use this in a very odd way. We take this equation right here and we will solve for the integrand. We're going to solve for that electric field by using the symmetries that we know exist for certain charge distributions. So if you have a charge distribution that is spherical, then that can be used. If you have a charge distribution that's cylindrical, then again, you can use Gauss's law to extract that electric field. Or if it's an infinite plane, you can again use that or exploit that symmetry and exploit Gauss's law to actually find the electric field. So Gauss's law is always true. It's Gauss's law. But like I said, using it the way we're using it, we're trying to extract that electric field out of the integrand. And in order to do that, we need these symmetries. Okay, if we don't have these symmetries, we can't do it. We can still use it. For instance, if we know the electric field and we know what surface we want to do a flux calculation over, we can still calculate the flux on the left-hand side, and that'll spit out what's equivalent to the charge enclosed divided by that epsilon naught that we've seen before. So it still works that way. Or we could use it in the reverse and say, well, I know what charge is enclosed, so I divide that by epsilon naught, and I know that's the total flux. So that's all well and good. Your book talks about a lot of different things you can do with it. I highly recommend you make sure you read this in chapter 22. But let's go ahead and do an example using Gauss's law. So the first thing I'm going to do is use Gauss's law to solve that problem we did the other day. So the other day we did an infinitely long wire. Now, being infinitely long and being a wire means that it's essentially a cylinder. Okay, so I'm going to again create a coordinate system, and this time the coordinate system is going to have the point on it along the y-axis and the wire along the z-axis instead of the other way around. I'm going to say there's my wire, and it goes on, of course, for infinity. So it's going to go on for infinity this way. Oops, evidently I've still got it on automatically make this drawing pretty. So it's going to go infinity that way. It's going to go infinity that way. And I'm going to say the charge per unit length, dang it, the charge per unit length is lambda, which is dq over dl. Okay. And I'm going to want to find the electric field. Actually, let's not do it there. Let's do it closer so I can fit it. Okay. I'm going to find the electric field at a distance r. Now, how I'm going to do that is using Gauss's law. So I'm going to state find, oops. So I'll just say find E, just leave it like that. So that's the problem. The solution is we're going to use Gauss's law, which says the closed integral of E dot dA, oops, is equal to Q enclosed over epsilon naught. So what we're going to do is we're going to draw a Gaussian surface. My Gaussian surface is going to go, basically it's going to go from this line, so about 2 there and then a little bit more. So I'm going to draw a Gaussian surface that looks like that, and I really wish I would have used the other button, but it looks like that. And then I'm going to use it again down here like that, and like that, and like that. And what I'm going to do is I'm going to say this length, oops, this length is L, and of course this radius is obviously R, the lowercase r. So it's basically a cylinder, even though it doesn't look like it because I screwed up this drawing a little bit. But anyways, that's supposed to be parallel. I don't know how that happened, but clearly I made a boo-boo. Let's see if I can do it. Nope, can't do anything with it, so I'll leave it be. All right, so that's our Gaussian surface. That's what it's called. And what I've done is I've chosen a Gaussian surface on which one, it's going to be closed. So I can't just imagine it's like our toilet paper roll. It's got to be the toilet paper roll with the cap on the top and the bottom. So it's more like a soup can, because otherwise it wouldn't be a closed surface. The other thing is I need all the surfaces to be perpendicular to the electric field or parallel, because if it's parallel, then I'll actually get a zero. So the left-hand side won't be a problem, but if it's perpendicular, then I'll actually get the electric field like I want it. So what I'm going to do is I'm going to make a hypothesis using my understanding of how Coulomb's law for electric fields and forces behaves. I'm going to make the hypothesis that the electric field E is in fact a electric field that only depends on the distance, the radial distance r from the z-axis, and that it points radially outward. So I'll put an r hat like that on it. Okay, that's my hypothesis. And I know that because one, we already solved it, but two, just a distribution of charge like that, that literally has every centimeter of this wire has the exact same amount of charge in it. So because I have that, I know that there's no way that, you know, some charge at the top is going to compel the electric field to have a strength in the negative z direction or in the negative x direction or the positive x direction. In fact, it's always going to be right in the y direction if I keep it on the y-axis. So I know that's the case. And I also know that the only parameter that matters is the perpendicular distance between the point and the axis of symmetry of the wire. So that's what I've actually done, I've chosen a hypothetical electric field that fits what I've learned about Coulomb's law. So now that I have that and I can use this Gaussian surface, then all I got to do is compute the left-hand side of Gauss's law, compute the right-hand side of Gauss's law, set them equal to each other, and solve for this E of R. So the left-hand side says the closed integral of E dot dA. Well, that's going to be equal to E. Now, it's a surface integral, just like the one we were just doing. So I've got to evaluate it on this red surface. And on this red surface, the radius is, in fact, R. So that's me applying the surface integral part. And then the dA, technically, I could go through and show you in cylindrical coordinates a perfect dA and then use a double integral and all that good stuff. I don't need to do that, okay? All I really need you guys to understand is that there's going to be a differential area dA, and the vector is going to be parallel to E, so it's going to point in the r hat direction. And the magnitude of it, I'm just going to call dA and then put it in r hat direction, because what's going to happen is, because this E of R is being evaluated on the surface, it's going to have a constant value and come out in front of the integral. And then I'm just going to have r hat dot r hat again, and then an integral of dA. So I'm integrating those little pieces that I just drew over that whole soup can label. But that just covers the soup label. So I'll put SL down here to remind you that this is the label of the soup can. It's got to be done over a closed surface. So I also have to go for the integral over the top. Now, in that case, it's a little more complicated. But for instance, you could say this little bit is dA. And again, I could work out what dA is, but I'm just going to call it dA k hat. And then if I go over here, the same thing's going to happen. Again, I could work out what that dA is, but I don't really need it. In this case, I'm going to say dA is equal to negative dA k hat, and it's negative because the k points down there. Remember, these vectors have to point out of the volume. So for the top, I'm going to get E of R, but R is actually going to vary, times r hat dot dA k hat, and I'll just say that varies because it's going to be a bunch of different r's from 0 to r, right? And then I also have an integral over the bottom again, it's going to be E of R, where R varies, dotted with negative dA K hat. And again, I'm going to say this part varies. Okay. Everybody understand why that's going to vary like that? So that's the soup label part plus the integral of dot 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 R hat dot K hat, which gives me 0, and that's over the top, plus the integral dot 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 R hat dot K hat, which again gives me 0. So what I ultimately get is just E of R times the area of the soup label, and the area of the soup label should be 2 pi R times L, right? Because if you cut a soup label straight down the side of the can, you lay it out, its width will be the circumference of the can, which is 2 pi R, and its height will be the height of the can, which is L. So everybody sees that the left-hand side is E of R times 2 pi RL. Now I showed you how to make the sausage, basically. Okay, I showed you all the details in here. Really, you should be able to jump from that first integral with the circle on it, showing me that you're taking into account the 3 parts, and then just jump to some E of R times an area. That's the left-hand side every time. It's just E of R times an area every time. Everybody remember that, because all this stuff is sort of voodoo. We're just making up stuff. We're actually understanding, hopefully, that there's some calculus behind it, but we know exactly how the calculus is going to play out, so that the left-hand side is just going to become a electric field magnitude times an area. That's what the left-hand side is always going to be. So write that down somewhere. You need that as understanding. Now, the right-hand side is the part that could be problematic. In this case, it's not bad, but the right-hand side is going to be Q enclosed over epsilon naught. Well, you know that the charge per unit length is lambda, and you know that the length is L. So can anybody tell me what charge is enclosed? The charge per unit length is lambda, and the length is L. So what charge should be enclosed?
Lambda times L.
Exactly. So you just write lambda L, and you put that over epsilon naught, and you're done. Okay. So now watch this. Left-hand side equals right-hand side. And when you do this, you get E of R, the magnitude of the electric field, times 2 pi RL is equal to lambda L over epsilon naught. So using our hypothesis, we see that the electric field E is actually equal to lambda. Notice the L's cancel out. Is equal to lambda over 2 pi epsilon naught R hat. And watch this for a second. I'm going to go back and look at the 242 on 921. And look at what we got. Lambda over 2 pi epsilon naught R times R hat. That was what we got when we did that nasty integral. See how much easier that was? So that's the beauty of Gauss's law, is you can use the symmetries and quickly come up with something like that. Anybody have any questions on that one? Okay. There's a ton of examples. I've put links to a couple of them on my YouTube channel. I'm going to show you another one next time as well. But right now I've only got about 10 minutes. So I'm going to choose an easier one to do. and it's related to the same one. We actually worked last time. I did that surface and I got this quantity, sigma over 2 epsilon naught times square bracket 1 minus 1 over the square root of z squared plus r squared k. Well, again, I told you, if you let z be really, really small compared to r, then this just reduces to sigma over 2 epsilon naught. I can use Gauss's law to show that automatically. So let's imagine again another coordinate system. I'll do this really quickly. Hopefully this will work out for you guys. I'm going to draw a coordinate system like so. And what I'm going to do is imagine a rectangular surface like this, like this, like this. And in fact, what I'm actually imagining is that this goes off infinitely far this way and infinitely far this way and this way and this way. Okay. In other words, you don't really have to have it be infinitely large. You just have to be so close that the distance from you to the plane is at least 1/10 or smaller than the distance to the edge. If you got that, it's going to come up pretty darn close. So I'm going to do that. I'm going to also switch to black so I can label this as my x-axis, y-axis, and this is my z-axis. And I'm going to say that it has a uniform charge distribution sigma, so that sigma is equal to dq over dA. In other words, the charge per unit area is just sigma. So we know that, for instance, if I wanted to talk about the electric field right here, you'd say, well, it's definitely got a z component. And you might think, well, wait a second, this could cause it to have a y component. But then you realize, well, wait a second, there's another one right here that's going to make it have the exact opposite y component, so it's going to cancel out. Similarly, you could assume it's going to have an x component, but again, back here is going to make the exact opposite x component. So you should ultimately reach the conclusion that the hypothesis is that the electric field is this. So E equals question mark. Solution. Hypothesis. E is equal to E of only z in the k hat direction for z greater than 0, and negative E of z in the k hat direction for z less than 0. And that's what I'm thinking is my hypothesis. In other words, I don't think it can depend on anything other than z, and it's only going to point in the positive z direction above it and the negative z direction below it. Now I can do the left-hand side. Left-hand side says the closed integral of E dot dA. So I've got to choose a Gaussian surface that is either parallel, the surface is actually parallel to the electric field so it cancels out, or it's perpendicular to the electric field so that it actually gives me an E times A. So the Gaussian surface I'm going to choose is in fact going to be the same thing that I used before, specifically a cylinder. And it's going to be a cylinder that cuts the plane in half so that actually half of it is above the plane and the other half is below the plane. And I'm going to say this area right here is A. Okay. So with that, I'm going to say the top has E of z k hat dotted with dA k hat, because you expect, of course, that it's going to be the same dA that we had earlier with the soup can, plus the integral over the bottom, which would be negative E of z k hat, because the electric field will point down, dotted with negative dA k hat, again, because the dA has got to point down. and then plus the integral over the soup label, which is going to have E of Z plus or minus, because some parts will be above the plane, some parts will be below the plane, K hat, dotted with dA, which is really going to depend on I hat and J hat. So you know that this part is going to in fact be 0, because the dA is only going to have I hat and J hat components, and the E has a K hat component. Does everybody understand how I reached the conclusion that the soup label has an integral equal to 0? Okay, so this is going to become E of Z integral dA plus E of Z. Notice the two negatives canceled out because you multiplied them. So this is going to become 2A times E of Z. And that's the left-hand side. Now, the right-hand side is Q enclosed over epsilon naught. Now, the charge per unit area is sigma, and the surface area parallel to that plane has an area A. So who can tell me what the charge enclosed will be? Anyone? So the charge per unit area is sigma. The area of the plane enclosed, you can see on the diagram, is obviously just the area of the top of the can, which is A.
The area times sigma.
Exactly. So we'll write sigma A over epsilon naught. That's the right-hand side. Now I do left-hand side equals right-hand side. And with that, that gives me 2A E of Z is equal to sigma A over epsilon naught. Now you see there's no Z dependence whatsoever. So I'm going to stop writing that E of Z completely and just call it E. But what you also see is the A's cancel out, and you get, again, using our hypothesis, the electric field is going to equal positive sigma over 2 epsilon naught K hat for Z greater than 0, and negative sigma over 2 epsilon naught K hat for Z less than 0. Notice there is a discontinuity, and this is actually a fundamental idea as well. Let me draw this real quick. I'm going to draw a plot of the electric field strength as a function of Z. So let's let this be Z, and let's let this be E. Then this quantity right here is going to be sigma over 2 epsilon naught. And for Z greater than 0, we're going to get exactly that. Now, if we come over here to this part, this is going to be negative sigma over 2 epsilon naught. And if we consider Z less than 0, then it's going to be over here like that. And you see the discontinuity from here to here. Equals sigma over epsilon naught. That's a fundamental rule. If you have a surface area, a surface charge, then it turns out the component of the electric field perpendicular to the surface will in fact be discontinuous by an amount sigma over epsilon naught. And this is just happening to be an example that shows that to us. Anybody have any questions here? All right, we got like 1 minute left, so let me show you something really quick that we need. if I put a positive plate here and a negative plate here, I would make what's called a capacitor. Okay. In this case, it's going to go right about there. And that's going to go back down like that. And there's a wire connected over here and a wire connected over here. So if you look from the edges of that, what you see, actually, let me try to do two different colors. I'm going to put a blue one over here to represent the negative. This one has a charge of negative sigma. This one has a charge of positive sigma. So if I talk about the electric field due to the positive plate, on this side, it'll point this way, and it will be sigma over 2 epsilon naught. On this side, it'll be this way, and it'll be sigma over 2 epsilon naught. Now, if we do the negative plate, you'll see that the electric field to the left will point towards the negative plate because the negative plate has a negative charge and positive charges are attracted to it. Similarly, this will be sigma over 2 epsilon naught towards the plate. And then also over here, we're going to have a electric field here that's sigma over 2 epsilon naught. And over here, we're going to have a electric field that is sigma over 2 epsilon naught. So what we see is E equals 0, E equals 0, but in the middle, we see E is equal to sigma over 2 epsilon naught plus sigma over 2 epsilon naught, which is the sigma over epsilon naught. And that's the electric field between plates of a parallel plate capacitor, and we're done. Okay. Now, I really need to show you, I've done a cylindrical symmetry. I've done a planar symmetry. I'm going to do at least one spherical symmetry. We can do coaxial cables, their cylindrical symmetry, all sorts of stuff. But I'm going to show you at least one more next time. But you basically have everything you need to complete chapter 22 now. Okay. I've adjusted the homework dates. They should be good to go. You guys are free to go. I will wait here for the last person to leave in case anybody has any questions. But other than that, have a good one, and I will see you guys on Thursday.
Hey, Professor. I sent you an email. I don't know if you got it. I sent it maybe a week or two ago.
Okay.
Yeah.
I think I remember seeing an email from you, Angelica. Yeah.
Yeah, I put Phys 242N. It was just about my the dateline or the due date for my first 2 assignments of class.
Oh yeah,
I gotten them done before that deadline you gave me.
Okay, gotcha. I thought I had replied to that because I do remember you saying that. So I evidently did read it, but yeah, let me check that. So you think it was your first 2 homework assignments? You probably got points deducted because they weren't done on time.
Yeah,
so
I think so. I'm not sure.
That's cool.
But if it doesn't make a big difference to my grade, then it's okay.
Yeah, no, it's definitely something I should fix. So I'll fix it. Don't worry about that at all.
Okay.
And I suspect if it happened to you, it happened to several people. And I know what happened in one case. So that's probably what it is. The same thing that happened in that one case happened in all of them. So I will do that. And I'm going to write a note to myself right now.
And then as for the midterm, will we be able to retake it, or is it are we keeping it there?
Okay, so yeah, that first face-to-face test, we're going to keep it there. But here's the deal. We're going to have another one. I think I found out the date was October 7th or 12th or something like that.
Okay.
Your syllabus. If you do better on that one, I'll replace that first score with
this. Thank you. Okay, I appreciate it. Because I suck at multiple choice. And I kid you not, all my original answers were the correct answers, but I had stayed there maybe for an extra 30 minutes. And I reselected all my answers and I screwed myself over. So yeah, thank you.
I normally try to do something like that anyways. But yeah, I'm going to do that for everybody. So don't fret it too much because that's really the whole reason I have 3 face-to-face tests is so that I could easily do that without feeling bad about it. And it normally takes 1 test for people to understand, oh, wow, this
relying too much on Chegg or relying too much on solutions that rather than me solving them myself initially can actually cause you to do less well on those face-to-face tests. So it just gives you a chance to regroup and reconsider. So don't worry about it.
Gotcha.
You got
All
a
right,
good chance to
thank
do well.
you.
You're
Appreciate
welcome,
it,
Angelica.
Professor. Have a good night.
You too. Taylor, you have anything?
No, sir. Have a good one.
You too. Take care. Bye-bye, everybody.